Every now and then, our star, the Sun, will set off an explosion larger and more energetic than any other in the entire solar system. Such is the energy released by these explosions that they create significant geomagnetic disturbances on Earth, often upsetting electrical systems and occasionally causing runaway weather effects. What are these explosions? They're called solar flares, and you may already be familiar with what they look like if you've ever seen a picture of the surface of the Sun. In this video, we're going to discover the amazing astrophysics behind solar flares and find out why and how they happen. Welcome back to 26 Dimensions, the space exploration and astrophysics channel here on YouTube. Don't forget to subscribe if you want to see my future videos. Solar flares are abrupt explosions of electromagnetic energy and hot plasma out from the surface of the Sun. They occur near dark spots on the star's surface, known as sunspots. These regions are much cooler and darker than the average brightness of the Sun, but they don't last long, eventually erupting into a flying tail of plasma. It is caused by the crossing and rearranging of magnetic field lines around these sunspots. The Sun releases a tremendous amount of energy due to the constant nuclear fusion reaction happening in its core. The temperature is so high that these gases, hydrogen and helium, are in a completely ionized state. This creates an optimum environment for nuclear fusion reactions to occur. 2 protons of hydrogen combine with 2 neutrons of hydrogen to form a helium nucleus. The helium nuclei are fused together to form increasingly heavy elements. This whole process generates trillions of joules of energy. When magnetic field lines cross and reorganize in the right way around a sunspot, a sudden explosion called a solar flare is caused. Solar flares release a great deal of radiation into space. If a solar flare is intense enough, it can interfere with electronics and radio communications here on Earth. Flares eject a ton of plasma and charged particles through the Sun's corona into outer space. They also emit a lot of radio waves, which can be detected by Earth-based equipment. If the ejection is in the direction of our planet, the particles can penetrate the upper atmosphere, the ionosphere, and cause bright aurora. From the Sun to Earth, the plasma may take several days to complete its journey. These explosions are classified according to their brightness in the X-ray region of the electromagnetic spectrum. There are generally 3 categories: X, C, and M-class flares. X-class flares are massive and cause major destructive events on Earth. M-class flares are still big, but cause substantially less damage, often just resulting in a few radio blackouts. C-class flares are very small compared to X flares and don't usually cause any abnormal effects on Earth. The most powerful solar flare ever recorded with modern methods was in 2003, during the Sun's last solar maximum, and it was so powerful that it overloaded the sensors measuring it. While this flare was powerful, M-class flares usually last longer and are more frequent. The minor solar flares, classed as C-type explosions, produce coronal mass ejections, but are often very slow and weak, taking a much longer time than bigger flares to die down. They rarely cause any significant geomagnetic disturbances here on Earth. High-frequency radio blackouts are the most common disturbances to occur on Earth when a significant solar flare erupts. Bursts of X-ray and extreme ultraviolet radiation are emitted during these events, which can add a great amount of noise to high-frequency radio bands on the sunlight side of our planet. It is usually the 3 to 30 MHz range that is most affected, although X-type flares can often influence the 30 to 300 MHz range. Radio blackouts are the most common space weather events to affect Earth, and also the fastest to happen. Minor events occur about 2,000 times each solar cycle, and the emission produced during flares take just 8 minutes at the speed of light to reach our planet. The blackouts tend to last several minutes, but can interrupt radio communications for several hours depending on the severity of the flare. So, an important question on our minds is when we're going to see the next massive solar flare. For how long will man-made electronics and communications be safe from solar weather before some huge X-class explosion causes chaos? Current methods of flare prediction are fairly unreliable, and there's no certain indication that any particular active region on the Sun will erupt. However, many sunspot properties and active regions correlate with flaring. For example, dark and magnetically complex regions called delta spots are prone to producing the greatest flares. Currently, we can analyze the fractal complexity of sunspot magnetic fields to get a good idea of whether a flare is going to happen within 24 to 48 hours. But this is only a probability, and sometimes unexpected flares happen. Our best chance of defending against this solar weather is making better predictions based on the science and shutting down infrastructure before a big eruption happens so our electronics aren't damaged so much. You've been watching 26 Dimensions, the space exploration and astrophysics channel here on YouTube. If you enjoyed this video explaining the phenomenon of solar flares, then you might be interested in some of my other videos. I'm a small YouTuber creating space and science videos. Don't forget to subscribe if you want to see my future uploads. Thanks for watching, and I'll see you next time.